Today, we're tackling a massive engineering challenge. I mean, a really high-stakes one. We're going deep, deep into the ocean to figure out how scientists are inventing a whole new kind of steel, a super steel, if you will, that's designed to survive in one of the most brutal environments you can possibly imagine.
Okay, so picture this. We're pushing energy exploration into deeper and deeper waters, trying to tap into these untouched reserves. But to do that, you need gear, you need pipes, you need components that can handle conditions that are just, well, they're almost unbelievable. And as this quote really drives home, we're not just talking about a small upgrade here. They needed a totally new class of material.
And just how extreme are we talking? We're talking about pressures of 20,000 pounds per square inch. That is an insane amount of force. It's basically the same kind of crushing power you'd find at the very, very bottom of the ocean. The engineering challenge here is just staggering.
So here's the bottom line. The steel we have now, the stuff that built our bridges and our skyscrapers, it's just not going to cut it. We've basically hit a wall. Our conventional materials, as good as they are, simply are not strong enough for this new frontier.
Now, what's so fascinating is that it's not just about the pressure. That's only part of the story. The real problem is this nasty combination of things. You've got the insane pressure, you've got scorching hot temperatures, and then you've got this really sneaky threat called hydrogen embrittlement. This is where tiny little hydrogen atoms can actually wiggle their way into the steel and make it super, super brittle.
And that brings us to the big question for today. How on earth do you invent a material that has never existed before? You can't just, throw a bunch of metals in a pot and hope for the best. You have to go all the way back to the basic science, to the atoms themselves. So how do you do it? Let's get into it. All right, section 1. To invent a new steel, first you've got to understand how all steel works. And it really all comes down to changing its internal structure, creating totally new arrangements of atoms that give it completely different properties. And every single one of these transformations starts with the process called nucleation. The best way to think about it is like planting a seed. It's that very first moment a tiny new crystal, a new phase, starts to grow inside the old steel. But here's the catch. For that little seed to actually sprout, it has to get over an energy hump. And this is a great way to look at it. On one hand, just creating the surface of that new crystal costs energy. That's like pushing a big boulder up a hill. But on the other hand, the new structure is more stable, and that releases energy. That's the boulders rolling down the other side. So nucleation only works if you have enough energy to get that boulder all the way to the top of the hill.
So once these new crystals start growing, they expand outwards until they run into each other. This is called hard impingement. It's pretty straightforward, right? It's just a physical collision. Think about the bubbles in a can of soda. They expand until they bump into their neighbors, and then they stop. It's the exact same idea.
But there's a much sneakier thing happening too, and it's called soft impingement. This is like an invisible collision. See, as each crystal grows, it's pulling in atoms from the area around it, creating this invisible zone. When those zones start to overlap, the crystals start fighting over the same atoms, and their growth slows down way before they even physically touch. So the takeaway is, to really control the steel, you have to manage both the physical collisions and these invisible turf wars.
Okay, so now we get the basic physics of how steel transforms. The next question is, how do scientists turn that knowledge into a tool they can actually use? How do they make a blueprint to predict what a new steel is going to do? They use a tool called a TT-togram diagram. Honestly, the best way to think of it is a roadmap. This chart tells a scientist for any recipe of steel, hey, if you cool it to this temperature and hold it for this long, you're going to get this crystal structure. It is an absolutely essential guide for treating steel. And if the TT diagram is the map, then the Avrami equation is kind of like the GPS that calculates all the routes. It's a formula that takes all that stuff we just talked about, the nucleation, the growth, the collisions, and it spits out a number that tells you exactly how fast a transformation is going to happen. It turns all that complicated physics into a practical prediction. And here's why all of this is such a game changer. With these models, scientists can stop guessing. They can design and test thousands of different steel recipes right on a computer before they ever have to melt a single piece of metal. This is the crucial part. By turning physics into code, we've moved from the old-school blacksmith's forge into the age of supercomputers, letting us design materials we couldn't have even dreamed of before. All right, so we have the theory, we have the computer models. Now let's bring it all back home. Let's see how scientists use this amazing toolkit to solve our original problem. creating a steel that can survive that nasty hydrogen embrittlement deep in the ocean.
You know, what's wild is that this isn't some new problem. Get this, scientists have known since 1875 that the real culprit is diffusible hydrogen. That means hydrogen atoms that are free to just wander around inside the steel. So the problem for over a century wasn't knowing what was causing the damage, it was figuring out how in the world to stop it.
So using their computer models, the researchers came up with this incredibly clever 4-step solution. Let's walk through it. First, they create a super strong base structure, kind of like a backbone, called martensite. Next, they carefully heat the steel just enough to sprinkle in these teensy tiny carbide particles. Now here's where the genius comes in. These particles are designed so they don't quite fit perfectly, and that creates these invisible little zones of strain all around them. And that leads to the final brilliant move. These strain fields act like microscopic traps, grabbing any hydrogen atoms that wander by and holding them tight. And what's the result? The hydrogen is completely locked down. It can't move. It can't get to the tip of a tiny crack and cause the whole thing to shatter. The very element that was the steel's biggest threat is captured and made totally harmless. The material is basically immunized against its own worst enemy. The real breakthrough here isn't just making a stronger steel. It's making a smarter one.
Okay, so having a brilliant design on a computer is one thing, but turning that idea from a lab into a massive, real-world piece of equipment, that is a whole other ballgame. This is where the true test of engineering begins.
And this timeline just shows you how huge that challenge is. You start with just an idea on a computer. Then maybe you make a tiny 200-gram sample, about the size of a hockey puck, to see if it even works. If that goes well, you scale up to a 100-kilogram ingot for some serious testing, and only after all of that can you even think about trying to make the final multi-ton component that's going to the bottom of the ocean. Every single step is a massive leap.
And this really brings us to the most important lesson of the whole project. In the world of real engineering, computer models and lab tests, they aren't enough. You haven't really succeeded until a full-size part has been built, put out into the real world, and proven that it can do the job. That's the only test that truly matters.
So, this amazing new steel solves a huge problem we're facing right now, but it really makes you wonder, right? What's next? From exploring deep space to building fusion reactors, what are the next epic challenges that are going to force us once again to invent the unbreakable materials of the future?